Picture this: a world without satellites, without telescopes, without even a simple calculator. Yet somehow, thousands of years ago, people looked up at the sky and not only mapped the stars, but predicted eclipses down to the minute. How? That's the mystery we're unraveling today. Ancient civilizations, from the Babylonians to the Maya, the Chinese to the Greeks, possessed a wisdom so precise, so advanced, that modern astronomers still study their work in awe. These weren't just guesses, they were calculated predictions, born from lifetimes of observation, intricate tools, and a deep, almost sacred understanding of the cosmos. And the most incredible part, they did it all with nothing but their eyes, their minds, and an unshakable curiosity about the heavens above. Think about what it must have been like to witness an eclipse in ancient times. No warning, no explanation, just the sun vanishing in the middle of the day, plunging the world into darkness. For many cultures, these events weren't just celestial phenomena. They were omens, messages from the gods, woven into myths and legends. But for the astronomers of the past, they were puzzles to solve. Through painstaking records etched into clay tablets, carved into stone, or painted on temple walls, they tracked the movements of the sun, moon, and stars, searching for patterns. And when they found them, they built entire systems around them: calendars, monuments, even cities aligned with the cosmos. Their achievements weren't just scientific, they were a testament to human ingenuity, a bridge between the earthly and the divine. So how did they do it? What secrets did they uncover that allowed them to foresee these cosmic events with such precision? That's the journey we're about to take. We'll explore the ancient observatories hidden in plain sight, the forgotten tools that acted as their calculators, and the stories they left behind, clues that reveal just how deeply they understood the universe. By the time we're done, you'll never look at the night sky the same way again, because this isn't just history, it's a reminder of what humanity is capable of when we dare to look up and wonder. Ready to step into the past and see the stars through their eyes? Let's begin. Long before the first written languages emerged, people were already tracking the heavens. In every corner of the ancient world, from the fertile plains of Mesopotamia to the dense jungles of Central America, civilizations developed their own ways of reading the sky. The Babylonians, for instance, didn't just watch the stars, they documented them with astonishing precision. Thousands of cuneiform tablets reveal their obsession with celestial patterns, noting the positions of planets and the timing of eclipses centuries before modern astronomy confirmed their accuracy. These weren't casual notes, they were mathematical records, some so detailed they could predict lunar eclipses within minutes. But why go to such lengths? For them, the sky was more than a scientific curiosity. It was a divine clockwork. Kings ruled by celestial omens, priests interpreted planetary alignments as messages from the gods, and farmers planted crops based on the phases of the moon. The Maya took this even further, carving their astronomical knowledge into stone. Their Dresden Codex, a fragile bark paper book, contains tables tracking Venus with near-perfect accuracy, proving they understood its 584-day cycle long before telescopes existed. And let's not forget the Chinese, whose court astronomers kept meticulous records of guest stars, what we now call supernovas, dating back to the 2nd century. What's truly remarkable is how these cultures, separated by continents and centuries, arrived at similar conclusions. The Great Pyramid of Giza aligns almost perfectly with true north, while England's Stonehenge marks the summer solstice sunrise. In Peru, the Nazca lines stretch across the desert, some pointing directly to celestial events. These weren't coincidences, they were deliberate, painstaking achievements, born from generations of watching, recording, and refining. And the tools they used, often nothing more than notched bones, shadow-casting sticks, or carefully placed stones. Yet with these simple instruments, they mapped the heavens in ways that still leave scientists in awe. So what drove this universal pursuit? Perhaps it was the human need to find order in chaos, to tame the unpredictability of nature by decoding its rhythms. Or maybe it was something deeper, a shared wonder at the vastness above, a longing to touch the divine. Whatever the reason, their legacy endures. Every time we check a calendar or marvel at an eclipse prediction, we're standing on the shoulders of those ancient stargazers who first dared to measure the immeasurable. The Babylonians didn't just stumble upon their eclipse predictions, they built them brick by brick, or rather, tablet by tablet. Imagine scribes hunched under the Mesopotamian sun, carefully pressing cuneiform symbols into wet clay, documenting every celestial event they witnessed. Over centuries, these records grew into an astronomical library, revealing patterns invisible to any single generation. One of their most groundbreaking discoveries was the Saros cycle, a rhythmic dance of the sun, moon, and earth that repeats every 18 years, 11 days, and 8 hours. By tracking this cycle, they could predict not just when an eclipse would occur, but whether it would be lunar or solar, partial or total. Their calculations weren't perfect, sometimes they missed by a few hours or miles, but for a civilization working without telescopes or even a concept of gravity, their accuracy was staggering. What's even more fascinating is how these predictions shaped their world. To the Babylonians, an eclipse wasn't just a shadow crossing the sky, it was a direct line to the gods. Kings relied on their astronomers like modern leaders rely on advisors, interpreting eclipses as divine warnings of invasions, famines, or the fall of dynasties. The Enuma Anu Enlil, a series of 70 tablets, served as their celestial playbook, linking specific eclipse patterns to earthly events. A solar eclipse might signal the king's death, while a lunar one could foretell a rebellion. Imagine the pressure on those court astronomers. A single miscalculation could mean the difference between peace and panic. Yet their work was so trusted that when they predicted an eclipse, the king would temporarily abdicate, replaced by a substitute king, to absorb the omen's wrath. After the event passed, the poor stand-in was quietly removed, a stark reminder of how high the stakes were. But the real genius of Babylonian astronomy lies in its longevity. These weren't short-term observations, they spanned generations. A single eclipse record might reference events 200 years prior, proving they understood the value of long-term data. Their methods spread across the ancient world, influencing Greek astronomers like Hipparchus and Ptolemy, who refined their models into the foundations of Western astronomy. Even today, the Saros cycle remains a tool for modern eclipse chasers. It's humbling to think that when we mark an eclipse on our digital calendars, we're using a system born from clay tablets and celestial omens. Now let's shift our gaze to the Nile, where the stars held a different kind of power. In ancient Egypt, astronomy wasn't just about prediction. It was woven into the fabric of daily life, from farming to faith. The heliacal rising of Sirius, the brightest star in the sky, signaled the annual flooding of the Nile, an event so vital it marked the start of their new year. Temples doubled as observatories, their corridors aligned with solstice sunrises, while pyramids served as eternal star maps, their shafts pointing to constellations tied to the afterlife. Where the Babylonians saw omens, the Egyptians saw order, a cosmos mirrored in the rhythm of their river and the journey of their gods. The Egyptians didn't just build pyramids, they built time machines. Those towering structures weren't just tombs for pharaohs, they were celestial compasses meticulously aligned with the stars. Take the Great Pyramid of Giza, for instance. Its four sides faced true north, south, east, and west with near-perfect precision, a feat that still baffles engineers today, but the real magic lies in the shafts inside. Two narrow corridors, barely wider than a person's shoulders, point directly to Orion's belt and the North Star constellations tied to Osiris, the god of rebirth. For the Egyptians, this wasn't just architecture, it was a cosmic roadmap for the pharaoh's journey to the afterlife. Then there's Sirius, the brightest star in the night sky. Every year, just before dawn in mid-July, it would reappear after a 70-day absence, rising moments before the sun. This event, called the heliacal rising, wasn't just a pretty sight, it was nature's alarm clock. Within days, the Nile would flood, coating the land in fertile silt. The Egyptians didn't just notice this pattern, they built their entire calendar around it. Their year began with Sirius's return, divided into 3 seasons: flood, growth, and harvest. It was so accurate that their 365-day calendar became the blueprint for the one we use today. But how did they track the stars so precisely without telescopes? The answer lies in their star clocks, intricate diagrams painted on coffin lids and tomb ceilings. These weren't just decorative, they were functional tools. By observing decans, groups of stars that rose in sequence throughout the night, priests could tell time like reading a celestial clock face. Each decan marked an hour, with 12 decans spanning the darkness. Over time, they noticed these star patterns shifted, leading them to adjust their calculations and refine their understanding of the cosmos. What's truly remarkable is how astronomy permeated every aspect of Egyptian life. Temples like Karnak were designed so the sun's rays would illuminate the inner sanctuary only on the solstice, a divine spotlight for the gods. Even the humble sundial, a simple stick casting a shadow, became a sacred instrument, linking earthly time to the heavens. This wasn't just science, it was a spiritual dialogue with the universe. Now let's journey east to ancient China, where astronomers didn't just chart the stars, they wove them into legends. While the Egyptians saw cosmic order, Chinese stargazers spotted celestial dragons and emperors in the night sky, blending meticulous observation with mythology in ways that shaped empires. In ancient China, the heavens weren't just a canvas of stars, they were a stage for cosmic drama. Picture astronomers in silk robes standing atop imperial observatories, watching as a shadow crept across the sun. To them, this wasn't merely an eclipse, it was a celestial dragon devouring the sun, a myth so powerful it shaped their understanding of the universe for millennia. The earliest records date back to the Shang dynasty, around 2,000 years before the Common Era, where oracle bones bear inscriptions like "the sun has been eaten." These weren't passive observations, they were urgent messages to the gods, often accompanied by rituals, beating drums, shooting arrows skyward to scare the dragon away. By the Han dynasty, around 200 years before the Common Era, Chinese astronomers had turned mythology into mathematics. They'd discovered the eclipse cycle of roughly 18 years, similar to the Babylonian Saros, but with a twist. Their calculations accounted for the moon's uneven motion, a breakthrough that let them predict eclipses within minutes. The imperial court relied on these predictions as matters of state. An unpredicted eclipse could mean the emperor had lost the mandate of heaven. One famous story tells of 2 astronomers, HSI and Ho, executed for failing to foresee a solar eclipse, proof of how seriously these celestial events were taken. But the real marvel wasn't just their math, it was their machines. While the Greeks had the Antikythra Mechanism, China had Zhang Heng's seismoscope, a bronze vessel adorned with dragons that could detect distant earthquakes. Though none survive today, historical texts describe astronomical devices just as intricate, like armillary spheres that mapped the heavens with rotating rings. The blend of poetry and precision was uniquely Chinese. They named constellations after imperial courtiers, saw the Milky Way as a celestial river, and recorded guest stars, supernovas, with such detail that modern scientists still reference their observations. What set Chinese astronomy apart was its seamless weave of myth and measurement. While Babylonian tablets focused on omens and Egyptian star clocks aligned with the afterlife, Chinese stargazers saw the cosmos as a mirror of their earthly empire, a realm of harmony where dragons and equations coexisted. Their legacy lives on in the world's oldest continuous astronomical records, a testament to humanity's endless quest to decode the sky. Now, let's cross the Pacific to the jungles of Mesoamerica, where the Maya turned temple rooftops into observatories and sacred books into star charts. While Chinese astronomers battled dragons, the Maya saw the cosmos as a vast, living calendar where every planet's motion held divine meaning. Their predictions were so precise they could forecast Venus's position 500 years into the future, all without a single metal tool. How did they achieve such accuracy? The answers lie in bark paper codices and pyramids aligned to catch the first light of the solstice. The Maya didn't just observe Venus, they worshipped it as a god, feared it as an omen, and wielded it like a weapon. Hidden within the fragile pages of the Dresden Codex, one of only 4 surviving Maya books, lies their most astonishing achievement, the Venus Table. This intricate chart, painted in vivid red and black glyphs, tracks the planet's movements with staggering accuracy, predicting its appearances as both the morning and evening star over a span of 500 years. To achieve this, Maya astronomers calculated Venus's synodic cycle, the time it takes to return to the same position in the sky, as 584 days, just 2 hours off from modern measurements. But this wasn't just math for math's sake. To the Maya, Venus wasn't a mere planet. It was Kukulkan's fiery twin, a celestial warrior whose rising could signal the perfect moment for battle. Kings and generals would wait for Venus to reach its brightest point before launching campaigns, believing the planet's glare would blind their enemies. The Dresden Codex even includes warnings glyphs depicting spears and death next to certain Venus positions, marking days when war would bring disaster. Imagine the pressure on those royal astronomers. A single miscalculation could doom an entire army. Yet their predictions were so reliable that centuries later, when Spanish conquistadors burned most Maya texts, the Venus Table's accuracy survived as proof of their genius. But Venus was just one piece of their cosmic puzzle. The Maya also mastered eclipses, weaving them into their long-count calendar, a system so precise it could pinpoint celestial events thousands of years in the future. Their eclipse tables, found in the same codex, reveal an understanding of the moon's erratic orbit that rivals modern astronomy. They knew, for instance, that eclipses occur in cycles of 173 days, a pattern they called the half-year rule. Temples like El Caracol at Chichen Itza were built as observatories, with narrow windows aligned to Venus's extreme positions and staircases marking solstice sunrises. Every carving, every pyramid was a stone calculator designed to harmonize earthly power with celestial rhythm. What's truly breathtaking is how they fused numbers with narrative. Where Babylonian tablets were clinical records, the Maya saw the cosmos as a story, a grand cycle of creation and destruction mirrored in the motions of planets. Their calendar didn't just track time, it prophesied it with the dreaded end date of December 21, 2012, misinterpreted by modern pop culture as a doomsday. In reality, it marked the reset of a vast cosmic cycle, akin to a celestial odometer rolling over. Their astronomy wasn't separate from their spirituality, it was the language of their gods. Now let's travel thousands of miles and thousands of years back to a windswept plain in England, where standing stones whisper secrets of the solstice. While the Maya charted Venus with paper and ink, the builders of Stonehenge used mammoth slabs of rock to capture the sun's journey, a feat of engineering that turned a barren landscape into a prehistoric planetarium. Rising from the Salisbury Plain like a frozen ring of giants, Stonehenge has puzzled historians for centuries, but beneath its towering stones lies a secret, one that might rewrite our understanding of Neolithic astronomy. While most visitors come to witness the summer solstice sunrise perfectly framed by the heel stone, few realize this alignment is just the beginning. The real mystery hides in 56 chalk pits circling the monument, known as the Aubrey Holes. Some researchers believe these weren't just ritual spaces. They were an ancient counting device, tracking the moon's subtle wobble across 18.6 years. This cycle, called the lunar standstill, marks when the moon rises and sets at its most extreme points on the horizon. And here's the astonishing part. By moving markers between these holes, Neolithic skywatchers could have predicted eclipses with startling accuracy. Imagine a world without writing, without metal tools, yet somehow, these builders grasped celestial mechanics that would stump modern astronomers without computers. The key lies in the Saros cycle, the same eclipse pattern the Babylonians later documented. Every 18 years, 11 days, and 8 hours, eclipses repeat in nearly identical sequences. While Stonehenge's creators left no written records, the Aubrey Holes align eerily with this rhythm. 3 full cycles around the circle would equal 56 holes, almost exactly matching the Saros period. Was this coincidence, or were these pits an eclipse calculator carved into the earth? The debate rages on, but one thing's certain: the monument's designers saw the sky differently than we do. To them, an eclipse wasn't just shadow meeting light. It was the cosmos breathing, a sacred alignment woven into the very stones they erected. Beyond eclipses, Stonehenge's astronomy reveals layers of sophistication. The station stones, 4 megaliths placed in a rectangle, align with the moon's southernmost rising and setting points during the standstill. Even the enigmatic slaughter stone, once thought a sacrificial altar, may have served as a lunar sightline when propped upright. This wasn't random stargazing. It was systematic observation spanning generations. Recent laser scans show axe carvings on the stones mirroring constellations, hinting that the entire site might be a 3-dimensional star map. What's truly humbling is realizing these achievements weren't isolated. From the Mayan temples to Egyptian pyramids, ancient cultures independently discovered similar celestial truths. Stonehenge stands as a testament to humanity's universal drive to decode the heavens, a drive that would soon ignite the golden age of Greek astronomy. While Neolithic Britons used stones to chase shadows, Greek thinkers would forge the first tools to measure them, blending celestial myths with mathematical rigor in ways that would shape science forever. The Greeks didn't just watch the stars, they measured them. While earlier civilizations saw celestial patterns as divine messages, thinkers like Thales of Miletus dared to ask how the heavens moved, not just why. Around 600 years before the Common Era, Thales shocked his contemporaries by predicting a solar eclipse, not through omens but geometry. Legend claims he halted a war between the Lydians and Medes when the sky darkened right on schedule. Whether true or not, the story captures a turning point, the moment astronomy began its shift from myth to mathematics. But it was Hipparchus, working on the island of Rhodes 3 centuries later, who transformed stargazing into a precise science. Armed with little more than a bronze instrument called a dioptra, he catalogued over 850 stars, noting their positions with unprecedented accuracy. His greatest breakthrough, discovering precession, the slow wobble of Earth's axis that makes the stars appear to drift over centuries. Imagine realizing without telescopes or satellites that the North Star hadn't always been Polaris and wouldn't always be. Hipparchus calculated this shift at 1 degree every 72 years, a figure just 7% off modern measurements. His star maps became the gold standard for over 1,000 years, guiding sailors and scholars alike. Then there's the Antikythera Mechanism, a corroded bronze relic pulled from a shipwreck in 1901. At first glance, it looked like a lump of rust. But X-rays revealed gears upon gears, an intricate clockwork universe. This hand-cranked device, likely built around 80 years before the Common Era, could predict eclipses decades in advance, track the Olympic Games cycle, and model the erratic motions of planets. Its precision gears accounted for the Moon's elliptical orbit, a concept not formally defined until Kepler in the 17th century. Think of it as the world's first analog computer, a masterpiece of engineering that fused Babylonian eclipse cycles with Greek geometry. What set Greek astronomy apart was its hunger for underlying principles. Where the Maya embedded math in mythology and the Chinese saw celestial bureaucracies, Greek thinkers sought universal laws. Aristarchus proposed a heliocentric solar system 2 millennia before Copernicus. Eratosthenes calculated Earth's circumference using shadows and simple geometry, coming within 2% of the correct value. Their genius wasn't just in observation, it was in daring to explain the mechanics behind the magic. This legacy didn't fade with the fall of Greece. When the Library of Alexandria burned, its knowledge scattered like embers, many caught by Islamic scholars who would fan them into new light. In Baghdad's House of Wisdom, astronomers like al-Battani refined Hipparchus's tables, while al-Sufi's Book of Fixed Stars preserved Greek constellations through the Dark Ages. The Antikythera Mechanism's gears may have rusted, but its spirit endured in astrolabes and water clocks, bridging ancient wonder with medieval innovation. Now consider this. Every time you check a weather app for moon phases or marvel at an eclipse forecast, you're tapping into a chain of knowledge stretching back to Thales's geometry and Hipparchus's star charts. The Greeks gave us more than myths, they gave us the tools to measure the cosmos itself. And as we'll see next, their work didn't just survive, it flourished in the hands of scholars who saw the heavens not as God's playgrounds, but as puzzles waiting to be solved. While Europe slept through its so-called Dark Ages, a revolution was unfolding under desert skies. In the bustling cities of Baghdad, Damascus, and Cairo, Islamic astronomers weren't just preserving Greek knowledge, they were transforming it. Take al-Battani working in 9th century Mesopotamia. While Hipparchus had calculated Earth's axial wobble centuries earlier, al-Battani refined it to near perfection using a massive mural quadrant, a curved wall instrument that could track stars with razor precision. His measurements of the solar year came within just 2 minutes of modern values, and his eclipse tables became the standard for medieval Europe. But here's what set Islamic astronomy apart. They didn't stop at observation. They built machines to measure what the naked eye couldn't. The astrolabe, a handheld brass computer, became their masterpiece. Picture a circular disc etched with star maps and rotating plates, slide them into position, and suddenly you could calculate prayer times, predict eclipses, or even determine the height of a mountain. Persian scholar al-Sufi took this further, creating celestial atlases so detailed they included Arabic adaptations of Greek constellations alongside Bedouin star lore. His Book of Fixed Stars didn't just copy Ptolemy's work, it corrected it, noting discrepancies in star brightness and adding new observations like the Andromeda Galaxy, the first recorded mention of this cosmic neighbor. What's often overlooked is how Islamic astronomy bridged science and spirituality. Observatories weren't separate from mosques, they were extensions of them. The famous Samarkand Observatory, built by Ulugh Beg in the 15th century, doubled as a religious school where students learned that studying the heavens was an act of devotion. Their calculations weren't just about accuracy. They determined the Qibla, the direction to Mecca, for prayers, and marked Ramadan's start by the crescent moon. Even their star names reveal this blend. Altair comes from Arabic for the flying eagle, while Betelgeuse means the giant's armpit, preserving both myth and measurement in the night sky. Now, imagine a different kind of celestial navigation, one without instruments or written records. As Islamic astronomers charted the heavens from marble towers, Polynesian voyagers were reading those same stars from wooden canoes, guiding themselves across thousands of miles of open ocean. Where scholars used brass astrolabes, these navigators relied on their hands, their memories, and an intimate dance with the waves. Polynesian navigators didn't just sail the Pacific, they danced with it. Picture this, a double-hulled canoe no wider than a modern SUV, cutting through swells taller than houses, guided only by the stars above and the whispers of the ocean below. No compasses, no maps, just generations of knowledge passed down through chants and stories, teaching sailors to read the night sky like a roadmap. They didn't just memorize constellations, they tracked their rising and setting points, creating a mental star compass divided into 32 directional houses. When clouds hid the stars, they tuned into subtler clues, the way waves refracted around islands, the flight paths of homing birds, even the shimmer of bioluminescence in their wake. This wasn't just navigation, it was a conversation with nature. Take the Hawaiian star line called Ki Ka o Makale, the canoe bailer of Makale. When these stars appeared upright, they signaled calm seas; when tilted, storms ahead. Navigators like Maupiilug, who famously guided the Hokulea canoe from Hawaii to Tahiti in 1976 using only traditional methods, described sensing islands miles away by the way ocean swells bent around unseen land. The real marvel, their voyages weren't accidental. They settled islands scattered across 10 million square miles of ocean with pinpoint accuracy, reaching remote dots like Rapa Nui, Easter Island, and Aotearoa, New Zealand, centuries before Europeans dared cross the Atlantic. What made Polynesian wayfinding unique was its fusion of astronomy and ecology. While Babylonian priests tracked eclipses for omens, these sailors studied the stars to feed their families. A star's position could reveal the best season to harvest breadfruit or when to expect migrating fish. Their knowledge was so precise that modern recreations of their voyages, like the Polynesian Voyaging Society's worldwide journeys, proved their techniques could consistently hit targets smaller than a pixel on Google Earth. This wasn't abstract science, it was survival coded into songlines where every constellation held practical lessons. Now, shift your gaze from the open ocean to the stone towers of the Andes. Just as Polynesians used stars to conquer the sea, the Inca wielded sunlight like a surveying tool. High above Cusco, pillars called sucancas acted as solar markers, their shadows creeping across ceremonial platforms to mark solstices and equinoxes. But these weren't just calendars, they were the empire's heartbeat, dictating when to plant, when to tax, even when to wage war. Where Polynesian navigators memorized the sky's rhythms, Inca astronomers etched them into the mountains themselves, turning entire landscapes into celestial clocks. High in the Andes, where thin air turns sunlight into liquid gold, the Inca engineered a celestial calendar out of living rock. Near Cusco, 12 mysterious pillars called sucancas stand sentinel on a hillside, not as mere monuments, but as precision solar markers. During the June solstice, when the sun reaches its northernmost point, shadows from these pillars would stretch perfectly across a ceremonial platform, signaling the start of the planting season. But their genius didn't stop there. The Inca built entire cities like Machu Picchu with windows and temples aligned to capture the sun's first rays on the winter solstice, turning stone into a sundial the size of a mountain. For the Inca, the sun wasn't just a star, it was Inti, the life-giving god whose favor meant survival. Priests monitored the pillars year-round, watching for subtle shifts in shadows that dictated when to sow quinoa or harvest potatoes. An eclipse, however, was cosmic chaos, a moment when the great jaguar of the underworld was said to devour Inti. Historical accounts describe panicked rituals during these events, sacrifices of llamas, offerings of gold, and the shrieks of priests trying to frighten the darkness away. The Inca even kept special black llamas reserved for eclipse ceremonies, believing their color could appease the angry skies. What's often overlooked is how their astronomy shaped an empire. Unlike the Maya's complex codices or Babylon's clay tablets, the Inca recorded celestial knowledge in quipus-knotted strings that tracked everything from harvests to eclipses. Their roads, stretching thousands of miles, doubled as solar sightlines, with way stations marking equinox sunrises. Even their warfare followed celestial rhythms. Campaigns launched when Venus appeared as the morning star, believing its light would blind enemies. This wasn't just stargazing, it was statecraft written in sunlight. Now, let's journey to ancient India, where astronomers didn't just predict eclipses, they calculated them down to the second using poetry. While the Inca carved shadows into mountainsides, Indian scholars penned Sanskrit verses so precise they could forecast lunar eclipses centuries in advance. Their secret, a blend of divine mythology and groundbreaking math that would later influence Newton himself. Imagine unrolling a palm leaf manuscript in 5th century Kerala, its inked verses revealing not hymns but algorithms. The Aryabhatiya, written by the mathematician Aryabhata in 499, contained formulas for eclipses so accurate they accounted for Earth's curvature, a concept Europe wouldn't grasp for another 1,000 years. His calculations treated the sky as a rotating sphere, with eclipse shadows cast by an invisible shadow planet he called Rahu. To Aryabhata, math wasn't separate from the cosmos, it was the language the gods used to move the heavens. But the real marvel was the Surya Siddhanta, a text so revered it was said to have been dictated by the sun god himself. This ancient manual didn't just describe eclipses, it provided step-by-step instructions to compute them using trigonometry. One verse explains how to calculate the moon's diameter during an eclipse by measuring the shadows, speed, a technique still taught in astronomy classes today. Indian astronomers even accounted for atmospheric refraction, noting how sunlight bends near the horizon, making the sun appear higher than it truly is. What set Indian astronomy apart was its seamless weave of science and storytelling. Eclipses weren't just equations, they were the demon Ra who swallowing the sun, only to have it pass through his severed neck, a myth explaining why darkness never lasted. Observatories like Jaipur's Jantar Mantar turned mythology into machinery, with colossal stone instruments that could track planetary motions to within fractions of a degree. While Western astronomers later credited themselves with discovering these principles, manuscripts prove Indian scholars had mapped them centuries prior, their knowledge carried westward by traders and translated into Arabic, then Latin. From the Andes to the Indus, these cultures shared one profound truth. The sky was never just a spectacle. It was a clock, a compass, a divine manuscript waiting to be read. And as we'll see next, this celestial conversation didn't end with the ancients, it echoes in the tools we use today, from smartphone apps to space telescopes, each one standing on the shoulders of those first stargazers who dared to measure the infinite. In the courts of ancient India, astronomy wasn't just a science, it was the heartbeat of empires. When the Surya Siddhanta declared that eclipses occurred when the shadow planet Rahu swallowed the sun, it wasn't merely myth, it was statecraft disguised as cosmology. Kings relied on these celestial predictions like modern leaders rely on economic forecasts, to time coronations, plant crops, and even wage wars. The Gupta Empire, under rulers like Chandragupta II, didn't just patronize astronomers like Aryabhatta, they embedded their calculations into the very fabric of governance. Imagine royal astrologers whispering to emperors that a lunar eclipse in the constellation of Mag has signaled coming turmoil, a warning that could alter the course of treaties or troop movements. Aryabhatta's breakthroughs went far beyond eclipse tables. His daring suggestion that Earth spins on its axis, written in lyrical Sanskrit verses, challenged centuries of dogma. While his contemporaries imagined elephants supporting a flat world, he calculated pi to 4 decimal places and described orbits with algebraic formulas. The real shock, he did this in 499, over a millennium before Copernicus. But here's what's often overlooked: his work wasn't confined to ivory towers. Sailors used his star charts to navigate the monsoon winds, while farmers planted pulses based on his solstice predictions. The Surya Siddhanta's trigonometry, which could pinpoint eclipse times within minutes, became the GPS of its era, guiding everything from temple construction to tax collection cycles. The ripple effects of Indian astronomy stretched across continents. When Arab scholars like Al-Khwarizmi translated Sanskrit texts in Baghdad's House of Wisdom, they didn't just adopt numbers, they inherited an entire worldview. The concept of zero, the sign function, even the zodiac signs we use today all bear the fingerprints of Indian astronomers. Later, when Jesuit missionaries brought these ideas to Europe, they ignited the scientific revolution. Kepler's laws of planetary motion echo techniques first penned on palm leaves in Kerala. Yet the true power of Indian astronomy lay in its duality. It was both poetry and precision, where the same text that described Rahu's severed neck also contained step-by-step instructions to calculate angular diameters. Observatories like Delhi's Jantar Mantar turned metaphor into mathematics. Its massive sundial, the Samrat Yantra, could tell time down to 2 seconds. This wasn't just stargazing, it was the codification of cosmic order, where every eclipse prediction reinforced the idea that the universe ran by rules even gods obeyed. Now shift your gaze from parchment to politics. When Emperor Akbar commissioned the Zij-i-Ilahi star tables, blending Hindu and Islamic astronomy, he wasn't just pursuing knowledge, he was unifying a kingdom under shared skies. Across dynasties, from the Mauryas to the Mughals, rulers knew one truth: whoever mastered the heavens ruled the earth. Their legacy endures every time NASA uses Aryabhatta's algorithms to calibrate satellites, or when modern eclipse chasers open apps built on principles scribbled in Sanskrit 1,000 years ago. The stars that guided ancient kings still steer us today, not as omens but as waypoints in humanity's unending quest to map the infinite. In ancient Babylon, an eclipse wasn't just an astronomical event, it was a political earthquake. When the moon's shadow blotted out the sun, kings would literally step down from their thrones, replaced by temporary, substitute rulers chosen to absorb the god's wrath. These unlucky stand-ins would rule for the eclipse's duration, sometimes even being sacrificed afterward to ensure the real monarch's safety. The message was clear: the heavens themselves had the power to make or break a reign. Across Mesopotamia, astronomers weren't just scientists, they were kingmakers, their clay tablet predictions determining when leaders should hide or when to launch military campaigns. The Hittites took this even further. Their texts describe solar eclipses as divine verdicts on royal legitimacy. One particularly dramatic event in the 14th century before the Common Era saw King Mercilli II interpret an eclipse as punishment for his father's sins, launching a series of desperate prayers and reforms to appease the storm god. In China, the stakes were just as high. The Bamboo Annals record how Emperor Zhong Kang executed his royal astronomers in 1900 before the Common Era for failing to predict an eclipse, a mistake framed not as scientific error, but as treason against the mandate of heaven. What made eclipses such powerful political tools was their unpredictability to the average person. While court astronomers might see patterns in their star charts, to the public, these events felt like sudden divine interventions. Clever rulers exploited this fear. The Maya would stage elaborate ceremonies during eclipses, with priests battling the darkness through ritual to demonstrate their connection to the gods. In ancient Rome, Augustus Caesar minted coins featuring his patron Apollo holding a solar disk after surviving an eclipse, turning celestial mechanics into imperial propaganda. Now compare these ancient manipulations to modern star maps, where Babylonian clay tablets marked eclipse paths with wedge-shaped symbols. Today's digital simulations can pinpoint solar shadows down to the exact street corner. Yet the basic principle remains unchanged. Knowledge of the heavens has always been power. The real difference: ancient rulers used eclipse predictions to control populations, while modern astronomers share them freely online. A democratization of celestial knowledge that would have stunned those Bronze Age kingmakers. The transition from omen to data reveals humanity's evolving relationship with the cosmos. Those early star maps, etched in stone or painted on tomb walls, weren't just navigation tools. They were the first attempts to codify the universe's chaos into something predictable, controllable. Today's satellite-guided maps may seem worlds apart, but they fulfill the same fundamental need: to transform the terrifying unknown into something we can measure, understand, and ultimately master. Buried beneath the sands of Mesopotamia for millennia, the Mul, Apin tablets are more than just ancient star maps. They're time capsules of human curiosity. These cracked clay surfaces, inscribed around 3,000 years ago, don't just list constellations. They plot the precise paths of planets like Jupiter and Venus across the night sky, marking their movements with a precision that would make modern astronomers nod in respect. Unlike today's digital catalogs, which compile millions of data points with telescopes and satellites, these tablets were crafted by scribes who relied solely on their eyes and meticulous record-keeping. Yet their observations were so consistent that when researchers compared MUL, Apin Jupiter positions to computer simulations of the ancient sky, the results matched within a few degrees, a margin of error smaller than the width of your pinky finger held at arm's length. What's even more striking is how these Babylonian astronomers organized the cosmos. Their constellations weren't the familiar Greek myths we know today, no Orion the hunter or Taurus the bull. Instead, they saw celestial plows, scorpion men, and the stars of E, a grouping tied to their water god, the Mul. Apin tablets didn't just map stars, they created a celestial calendar, dividing the sky into 3 parallel roads, tracking the paths of the moon, sun, and planets. Each entry reads like an ancient GPS instruction. When the Pleiades rise, start sowing barley. For them, astronomy wasn't abstract science, it was the rhythm of daily life, dictating everything from harvests to temple rituals. Fast forward to today, where projects like the Sloan Digital Sky Survey have catalogued over 1 billion celestial objects with robotic telescopes. The scale is unimaginably larger, but the goal remains eerily similar: to make sense of the universe's patterns. Modern star catalogues still use Babylonian concepts like ecliptic coordinates, the sun's apparent path across the sky, proving that some ideas transcend millennia. Even the way we number stars traces back to their methods. The bright star Aldebaran, for instance, is still designated Alpha Tauri, a naming convention rooted in ancient traditions. Yet there's a poetic contrast in how we access this knowledge today. Where Babylonian scribes needed years to compile a single tablet, anyone with a smartphone can now pull up a real-time sky map augmented by GPS. But strip away the technology, and the essence is unchanged. Both eras share that same primal urge to look up and decode the darkness. The real magic lies in realizing that when you check an app to spot Jupiter tonight, you're completing a chain of observation that stretches back to astronomers who wrote on clay instead of silicon. Now, let's step inside the places where these ancient stargazers worked, the observatories that served as their cosmic laboratories. From the shadowy corridors of Egyptian temples to the towering platforms of Mayan pyramids, these structures weren't just buildings, they were machines built to capture the sky's secrets, stone by deliberate stone. Standing atop the pyramid of El Caracol at Chichen Itza, you wouldn't just see a ruined staircase, you'd be standing inside a working astronomical instrument. The Maya designed this spiraling tower not as a temple, but as a precision observatory with narrow windows aligned to Venus's most extreme rising and setting points. Every step, every angle was calculated to catch celestial events like cosmic clockwork. But this wasn't unique to the Maya. Across the globe, from Cambodia's Angkor Wat to England's Stonehenge, ancient architects baked astronomy into stone, creating megastructures that doubled as celestial calendars. Take Angkor Wat's sprawling temple complex. At dawn on the spring equinox, the sun rises directly over its central tower, casting a shadow that aligns perfectly with the causeway, a phenomenon that still draws crowds today. The builders didn't just orient the temple for beauty, they encoded the solar year into its very foundations. Even the surrounding moat acted as a reflecting pool, doubling the sky's spectacle on its mirrored surface. Similarly, Egypt's great temple of Ammon at Karnak was designed so the winter solstice sun would illuminate its inner sanctum, spotlighting the statue of the god like a divine spotlight. What's astonishing is how these cultures, separated by oceans and millennia, arrived at similar solutions. The Pueblo people of Choco Canyon built their great houses with walls aligned to lunar standstills, while Cambodia's Bayon Temple features towers arranged to mark the solstices. These weren't accidental alignments, they were the result of generations of observation refined into architecture. The common thread, a belief that celestial rhythms governed earthly life from harvests to sacred ceremonies. Now consider the practical genius behind these designs. Without steel or glass, ancient builders used shadows, light shafts, and geometry to turn stone into scientific instruments. Newgrange in Ireland, a tomb older than the pyramids, features a roof box that floods the inner chamber with winter solstice sunlight for exactly 17 minutes each year. The precision is staggering. Modern engineers using lasers struggle to replicate its alignment. These structures weren't just symbolic, they were functional tools that dictated planting seasons, religious festivals, even the timing of wars. The deeper you look, the more layers emerge. Recent LiDAR scans of Guatemala's Tikal reveal that its pyramids were positioned to mirror the Pleiades star cluster during key dates, while Peru's 13 towers of Chanquillo functioned as a solar calendar, marking the year's progression with sunrise and sunset positions. Each civilization adapted the same principles to their landscape and beliefs, proving that astronomy wasn't just a science, it was the language of power, faith, and survival. Now imagine the minds behind these monuments. They had no satellites, no calculators, yet they mapped the heavens with nothing but patience and stone. Their legacy isn't just in the alignments we can still measure today, but in the realization that the sky was humanity's first clock, compass, and scripture written not in ink, but in shadows and light. The Mayan Hob calendar didn't just count days, it orchestrated an empire. Imagine a society where the timing of every harvest, every royal coronation, even every battle hinged on the precise alignment of Venus or the solstice sun. This 365-day solar calendar, interlocked with the sacred 260-day Tzolk'in, created a 52-year cycle known as the calendar round. Priests would climb the steps of El Castillo at Chichén Itzá, watching as the equinox sun cast serpentine shadows down the pyramid sides, signaling it was time to plant maize or hold the new fire ceremony. But the real genius lay in its correction system. Unlike the Julian calendar, which drifted by days each century, the Maya accounted for the solar year's extra quarter day by subtle adjustments woven into their long count, a precision that kept their celestial clock in sync for millennia. Meanwhile, along the Nile, the Egyptian civil calendar turned astronomy into bureaucracy. Their year, fixed at 365 days, was divided into 3 seasons: inundation, growth, and harvest, each tied to Sirius's heliacal rising. When the dog star reappeared before dawn in mid-July, it wasn't just a celestial event, it was tax season. Scribes would fan out across the floodplains, assessing grain yields based on stellar timetables. Yet this simplicity came at a cost. With no leap years, their calendar slipped backward through the seasons, completing a full cycle every 1,460 years, a quirk the Greeks later called the Sothic cycle. Half a world away, Chinese astronomers faced a different challenge. Their lunisolar calendar had to reconcile moon phases with solar years, inserting extra months every few years to keep seasons aligned. Emperors employed entire bureaus of astronomers, whose predictions of eclipses and comets were considered signs of heavenly favor. The Shang dynasty's oracle bones reveal eclipse records so meticulous they've helped modern scientists calculate Earth's slowing rotation over millennia. Now let's shine a light on the often overlooked architects of these systems, women. While history books highlight male astronomers like Ptolemy or Copernicus, ancient star knowledge was often held by priestesses and queens. In Mesopotamia, the Nadatu women of Sippar, cloistered priestesses of the sun god Shamash, maintained detailed eclipse records on cuneiform tablets, their observations crucial to Babylonian prediction models. Over in Egypt, Cleopatra wasn't just a ruler. She authored astronomical treatises and likely influenced Caesar's Julian calendar reform. Perhaps most striking were the Maya's moon goddess scribes. Recent decipherments of painted vases show women in royal courts recording eclipse tables, their calculations as precise as their male counterparts. One noblewoman from Palenque, Lady Yol Icknall, may have even used Venus cycles to time her military campaigns. These women didn't just observe the cosmos, they wielded it, turning celestial patterns into tools of power long before telescopes existed. From the observatories of priestesses to the star charts of queens, their legacy reminds us that the sky was never just a man's domain. It was a shared canvas where the strokes of countless forgotten women helped paint humanity's first maps of time itself. Hypatia of Alexandria wasn't just a scholar, she was a revolutionary. Walking the marble halls of the great library in the 5th century, she taught astronomy, mathematics, and philosophy to eager students, both men and women, at a time when most female intellects were sidelined. Her celestial observations built on Ptolemy's work, refining star charts with meticulous precision, but her legacy extends beyond equations. She designed astrolabes' brass models of the heavens to help sailors navigate by the stars, blending theory with tangible tools. Tragically, her life ended in violence, a victim of rising tensions between science and dogma. Yet her story shatters the myth that ancient astronomy was solely a man's pursuit. Far to the east, another group of women left their mark on the stars. In Tang Dynasty China, court astronomers like Wang Zhenyi defied convention by mastering celestial mechanics. Zhenyi, born in 1768, penned treatises explaining lunar eclipses with startling clarity, using nothing more than a lamp, a mirror, and a table to model Earth's shadow. Her writings demystified the cosmos for laypeople, proving that scientific understanding wasn't confined to imperial observatories. Meanwhile, in Korea, Queen Seondeok of Silla built Cheomseongdi, the oldest surviving astronomical tower in East Asia, its 27 stone layers symbolizing her reign's alignment with celestial cycles. These women weren't anomalies, they were part of a hidden tapestry. Mesopotamian Nadatu priestesses tracked Venus cycles for temple rituals, their records later used by Babylonian astronomers. In medieval Europe, abbesses like Hildegard of Bingen mapped the stars alongside composing hymns, seeing no divide between faith and science. Even in the Americas, Maya moon priestesses painted eclipse tables in sacred codices, their predictions guiding kings. Their collective work proves a profound truth. The history of astronomy isn't a straight line of lone geniuses, but a constellation of collaborators, many erased by time. Now turn your gaze from star charts to storytelling. When ancient artists painted eclipses on cave walls or poets wove them into epics, they weren't just documenting events, they were processing the unknown. The Norse saw the sky wolf skull chasing the sun. The Inuit believed the moon goddess Malina fled her brother's wrath. These tales, etched in pigment and verse, reveal how deeply eclipses stirred the human imagination. A Chinese silk painting from the Han Dynasty captures a solar eclipse with dragons coiled around the sun, while Greek playwrights like Aristophanes used eclipses as plot twists, signaling divine intervention. Art became a bridge between fear and understanding. In the Lascaux caves, red ochre dots may depict the supernova of 5,000 years ago. The Dresden Codex's eclipse tables aren't dry data. They're illuminated with gods battling darkness, transforming math into myth. Even Shakespeare harnessed eclipses for drama. In King Lear, Gloucester blames his son's betrayal on these late eclipses, mirroring Elizabethan superstitions. Each brushstroke and quill line preserved not just celestial events, but the emotions they evoked: awe, terror, wonder. What emerges is a portrait of astronomy as a deeply human endeavor. Whether carved into clay by a Babylonian priestess or painted by a Maya scribe, these records remind us that the stars were never just points of light. They were stories, warnings, and guides woven into the fabric of cultures across millennia. And as we'll see next, those stories didn't just live in the past. They sparked the revolutions that would birth modern science. The Norse weren't just frightened by eclipses, they wove them into epic battles between light and darkness. Their myths told of Skirl, a monstrous wolf eternally chasing the sun across the sky, finally catching it during an eclipse with jaws that shook the heavens. Meanwhile, halfway across the world, Aboriginal Australians described eclipses as the sun woman being swallowed by the moon man, only to re-emerge when ancestral spirits intervened. These weren't just stories, they were survival tools, transforming celestial chaos into narratives humans could process. In Vietnam, people banged drums to scare away the frog devouring the sun, while the Inca sacrificed black llamas to pacify the angry sky. Every culture's eclipse myth shared a common thread: the desperate need to explain why light could vanish without warning and how to bring it back. But behind these myths lay something even more fascinating: meticulous observation. The same cultures that spun tales of celestial monsters were also quietly recording patterns. Take the Aboriginal Gulumaurigin people of northern Australia. Their oral traditions didn't just personify eclipses, they encoded warning signs, like specific bird calls or shifts in wind direction, that often preceded the event. Recent research suggests these cues, passed down through songlines, may have helped communities predict eclipses long before written records existed. Similarly, Norse navigators noted how eclipses coincided with certain star positions, turning myth into a rough forecasting system. The real turning point came when these observations met mathematics. Ancient Greek poets like Archilochus wrote of eclipses as divine omens, yet by the time of Thales in the 6th century BC, thinkers began seeking physical causes. This shift from myth to measurement didn't erase the stories, it layered them. The Maya kept their eclipse demons in the Dresden Codex but paired them with tables so precise they could project lunar shadows centuries into the future. Their tools, not telescopes or computers but knotted strings, pebbles arranged in counting grids, and the most powerful instrument of all, human patience. Consider the humble gnomon, a simple stick casting a shadow. In China, astronomers used these to measure the sun's height, noting subtle changes that hinted at upcoming eclipses. The Babylonians took it further, tracking shadow lengths on clay tablets over decades until patterns emerged. These weren't just random notes, they formed the world's first known mathematical models for eclipse prediction. One Babylonian tablet from 323 BC even includes a step-by-step guide. Multiply the time since the last eclipse by 1.035, then add 18 years and 11 days. The result, predictions accurate to within hours, a feat unmatched for centuries. The genius of these tools lay in their simplicity. Without lenses or gears, ancient astronomers turned everyday objects into precision instruments. The Greeks used the dioptra, a simple sighting tube, to measure lunar positions. Persian scholars refined the astrolabe, a handheld disc that could calculate eclipse times based on star angles. Even Stonehenge's massive stones, when aligned with Aubrey holes, may have functioned as a Neolithic eclipse calculator, using movable markers to track celestial cycles. What's striking is how these tools transcended borders. The same math Babylonian scribes pressed into clay appeared centuries later in Mayan bark books and Chinese silk scrolls, proof that human curiosity follows universal rhythms. Whether carved in stone or sung around campfires, our ancestors' eclipse stories and tools reveal a truth far deeper than myth or math alone. The unshakable belief that even the darkest moments could be measured, understood, and ultimately illuminated. The simplest tools often held the greatest power in ancient astronomy. Take the gnomon, just a stick planted in the ground, yet this unassuming tool became humanity's first protractor for the sky. By tracking the length and direction of its shadow, Egyptian and Chinese astronomers could measure the sun's height at noon, marking solstices when shadows stretched longest or shortest. But the real breakthrough came when they noticed something extraordinary. Gnomon shadows didn't just change daily, they traced graceful curves over seasons, revealing Earth's tilted axis centuries before telescopes confirmed it. In China's Zhou dynasty, court astronomers used gnomons to determine the exact length of a solar year, correcting their calendar with precision that rivaled later European models. Then came the astrolabe, a handheld marvel that transformed stargazing into a portable science. Persian scholars like al-Biruni refined these brass discs into celestial computers, their rotating plates etched with star maps and altitude scales. Turn the reter, a pierced metal web representing the heavens, to match the night sky, and suddenly you could calculate prayer times, predict sunrise, or even measure the height of a mountain. What made the astrolabe revolutionary wasn't just its accuracy, but its versatility. Sailors navigated monsoons with it, architects aligned temples by it, and poets like Chaucer wrote instruction manuals for it. This wasn't just a tool, it was a bridge between the cosmic and the practical. But the crown jewel of ancient instruments was the armillary sphere. Picture a skeletal globe of interlocking metal rings, each representing a celestial circle, the equator, the ecliptic, the horizon. Greek astronomers like Hipparchus used these spheres to model planetary motions, while Chinese versions featured delicate dragons cradling the rings in their claws. The real genius lay in their adaptability. Remove a ring to focus on the moon's path, add one to track Jupiter's retrograde loops. When Ptolemy described the cosmos as nested spheres, he wasn't speaking metaphorically. He was documenting the armillary's physical design. These devices didn't just predict eclipses, they visualized the very machinery of the heavens. Yet for all their sophistication, these tools were born from humble observations. The quadrant, used to measure star angles, evolved from the gnomons' shadow tracking. The Merkhit, an Egyptian sighting tool made from a palm rib and plumb line, became the precursor to modern theodolites. Even Stonehenge's megaliths functioned as a colossal stone gnomon, marking solstices with silhouettes cast by the heel stone. What tied these inventions together wasn't complexity, but curiosity, a relentless drive to quantify what others saw as divine. Now, let's dispel a persistent myth. Ancient astronomers weren't just mystics staring at the sky. The Maya calculated Venus's orbit within 2 hours over 5 centuries. Babylonian scribes computed Jupiter's speed using geometry we'd now call calculus. When Hipparchus mapped star positions in the 2nd century BC, his error margin was smaller than the width of a full moon. These weren't lucky guesses, they were the result of meticulous record-keeping, iterative improvements, and instruments refined over generations. The real magic wasn't in the stars themselves, but in the human ingenuity that decoded their dance, one shadow, one gear, one observation at a time. The idea that ancient civilizations needed extraterrestrial help to understand the cosmos doesn't just underestimate human ingenuity, it erases the centuries of painstaking observation and innovation that truly unlocked the stars. Look at the Maya, who calculated Venus's orbit with near-perfect accuracy using nothing but knotted strings and stone markers. Or the Babylonians, whose eclipse predictions relied on generations of scribes meticulously recording celestial events on clay tablets. These weren't gifts from alien visitors, they were hard-won victories of human persistence. The real story isn't about advanced technology handed down from the skies, it's about people sitting under the night sky, night after night, decade after decade, connecting the dots until the patterns became clear. Modern science, for all its sophistication, still follows the same basic principles those ancient astronomers pioneered. Today's satellite-powered star maps and supercomputer simulations may seem worlds apart from Babylonian clay tablets, but the core method remains unchanged. Observe, record, analyze, repeat. When NASA predicts an eclipse down to the second, it's using mathematical models refined from the same Saros cycle the Babylonians discovered. The Hubble telescope's deep-field images owe a debt to Hipparchus, who catalogued star positions over 2,000 years ago with nothing but a bronze dioptra. Even the algorithms in your smartphone's astronomy apps trace their roots back to Aryabhata's trigonometric calculations in ancient India. What's truly remarkable is how these early breakthroughs stand up to modern scrutiny. Recent studies comparing Maya eclipse tables with contemporary data found their predictions off by mere hours, astonishing precision for a civilization without telescopes or calculus. Similarly, when researchers tested Stonehenge's alignment using laser scans, they confirmed its solstice markers were accurate to within a fraction of a degree. These weren't lucky guesses, they were the result of methodical, repeatable science. The tools may have been simple shadow sticks, knotted ropes, aligned stones, but the thinking was anything but primitive. The real difference between then and now isn't intelligence or capability, it's scale and speed. Where ancient astronomers spent lifetimes compiling data, modern telescopes like the James Webb capture cosmic details in seconds. But the essence of discovery hasn't changed. Just as the Inca used Sukanka pillars to mark the sun's journey, today's astronomers use quantum detectors to track photons from the edge of the universe. Both approaches share the same goal, to measure the immeasurable and make the unknown familiar. So the next time you hear someone claim ancient feats were too advanced for humans alone, remember the scribes who spent decades etching star positions into clay, the navigators who crossed oceans by memorizing wave patterns, or the builders who aligned pyramids to celestial events with nothing but shadows and patience. Their achievements weren't handed down from the stars, they were built from the ground up, one observation at a time, by people who refused to stop looking up. And that's a legacy far more inspiring than any alien intervention. Ancient astronomers peering at the sky and modern scientists programming supercomputers might seem worlds apart, but their eclipse predictions share an unexpected kinship. Today, NASA calculations can pinpoint a solar eclipse's path down to the width of a city block, using satellites tracking the moon's micron-level wobbles. Yet 3,000 years ago, Babylonian scribes staring at the same sky came shockingly close. Their clay tablet predictions often hit within hours, sometimes even minutes. The real difference wasn't brilliance, it was bandwidth. Where modern astronomy crunches terabytes of data in seconds, ancient scholars relied on centuries of handwritten records, passed down through generations like a slow-motion relay race. Take the Babylonian Saros cycle, a rhythmic celestial pattern repeating every 18 years, 11 days, and 8 hours. By tracking this cycle across lifetimes, they could forecast eclipses with startling reliability. One tablet from 323 years before the Common Era even includes corrections for seasonal variations, proving they understood their calculations weren't perfect. Fast forward to today, and that same Saros cycle still underpins eclipse predictions, only now it's fed into algorithms accounting for Earth rotation slowdown and the Moon's retreating orbit. The core insight remains identical. We've just added more decimal places, but perhaps the most humbling comparison lies in the tools. The Maya used strings and beads to model Venus's orbit, while modern astronomers deploy space-based lasers measuring the Moon's distance to within millimeters. Yet both methods converge on the same truth: celestial motion follows rules, not whims. When the ancient Greek Antikythra Mechanism, a bronze gearbox from 80 years before the Common Era, could predict eclipses decades ahead, it wasn't magic. It was mechanics painstakingly engineered by observing patterns others missed. The real legacy of these early astronomers isn't just in what they got right, it's in how they thought. Without the concept of gravity, Babylonian scholars still deduced eclipse seasons. Without telescopes, the Maya calculated lunar cycles to within hours. Their achievements whisper a vital lesson. Scientific progress isn't about having all the answers up front. It's about asking the right questions persistently enough that even wrong assumptions, like the Babylonian shadow planets thought to cause eclipses, can lead to startling accuracy. Now picture this knowledge teetering on the edge of oblivion. As empires crumbled, libraries burned, and languages faded, millennia of celestial observations nearly vanished into ash and dust. The Great Library of Alexandria, where Hypatia refined Ptolemy's star charts, went up in flames. Mayan codices, save a handful, were torched by conquistadors. Even Stonehenge's purpose faded into myth, yet fragments survived scratched into clay, hidden in tombs, or passed orally across generations. These fragile threads, clinging against time's erosion, would one day reweave humanity's connection to the stars. The flames that consumed the Library of Alexandria didn't just burn parchment, they erased centuries of human curiosity. Imagine shelves buckling under the weight of star charts from Babylon, Egyptian water clocks that measured night hours by celestial movements, and treatises by scholars like Hypatia, who mapped the cosmos with nothing but bronze instruments and sheer intellect. This wasn't just a building lost, it was a fracture in humanity's collective memory, and Alexandria was hardly alone. When Spanish conquistadors burned Maya codices in the 16th century, they reduced thousands of years of eclipse predictions and Venus tables to ashes in a single day. Only 4 Mayan books survived, their fragile bark pages whispering secrets we're still deciphering. Yet against all odds, fragments endure. Ptolemy's Almagest, written in the 2nd century, somehow slipped through history's cracks, preserving Greek and Babylonian astronomy in its star catalogues and geometric models. But here's the haunting truth. We're reading a palimpsest of knowledge, a text where layers have been scraped away. Ptolemy himself built on Hipparchus's lost works, just as Islamic scholars later refined Ptolemy's errors in observatories from Baghdad to Cordoba. Each generation's breakthroughs were shadows of something grander that came before and vanished. The real tragedy isn't just what was lost, but how close we came to losing everything. Take the Surya Siddhanta, India's ancient astronomical masterpiece. Surviving copies date back only to the medieval era, yet its roots stretch to the Gupta Empire, where mathematicians calculated Earth's circumference with eerie precision. Or consider the Dresden Codex, that lone Mayan book with Venus tables so accurate they rival modern ephemerides. Had a single ship carrying it sunk, had one more library fallen, we might never have known these civilizations peered as deeply into the cosmos as we do. This fragility holds a mirror to our own era. We digitize texts and beam probes into space, yet how much of our knowledge exists as fleeting electrons on vulnerable servers? The Babylonians pressed their star records into clay, a medium that survived millennia in rubble. Today's hard drives may not last a century. There's poetry in realizing that the most resilient backup system for modern astronomy might still be paper, just like the Almagest's medieval scribes who copied it by candlelight. What these shattered legacies teach us isn't just about the past, it's about stewardship. When Timbuktu's librarians hid centuries of astronomical manuscripts in desert caves during invasions, or when monks in Byzantium painstakingly transcribed Greek texts while empires collapsed around them, they were doing more than preserving words. They were holding open a doorway between eras, ensuring that a future age could stand on their shoulders. That chain of transmission, from clay tablet to parchment to pixel, is the true miracle of astronomy's history. Not the discoveries themselves, but the fact that we can still read them. Now, let's step back from the brink of loss to celebrate the victories. Every time an archaeologist brushes dust off a cuneiform eclipse record, every time a historian deciphers a faded star map in a medieval Arabic manuscript, we reclaim a piece of that shattered mosaic. These fragments remind us that knowledge isn't just power, it's a torch passed hand to hand across darkness. It's light surviving against all odds, and that torch still burns today, not in libraries or observatories, but in every curious gaze turned upward to the stars. There's something almost radical about the way ancient astronomers worked. No satellites, no algorithms, just the slow, steady accumulation of knowledge over lifetimes. Picture a Babylonian scribe etching eclipse records into clay, knowing he'd never live to see the full pattern emerge. Or a Maya priestess tracking Venus across decades, her observations woven into a tapestry only future generations could complete. Their greatest tool wasn't technology, it was patience, a willingness to let the cosmos reveal itself on its own terms. In our age of instant answers, where a smartphone can summon star maps in seconds, their deliberate pace feels like a lost art. Yet buried in their methods are lessons we've never needed more. Consider the sheer discipline of their observation. The Babylonians didn't just glance at the sky, they kept meticulous diaries, noting planetary positions night after night for centuries. One tablet from Uruk records Jupiter's movements with such precision that modern astronomers used it to measure changes in the planet's orbit over millennia. The Maya, too, treated astronomy as a team sport, generations of scribes adding to codices like the Dresden, each building on the last's work. This wasn't solitary genius, it was collaborative science at its purest, where progress meant passing the torch. Even Stonehenge's alignments, refined over centuries of trial and error, speak to a culture that valued collective memory over quick results. What's striking is how their limitations became strengths. Without telescopes, they trained their eyes to catch subtle shifts, a star dimming slightly before an eclipse, or Venus pausing in its path. The Polynesians, navigating vast oceans, learned to read wave patterns and bird flights as celestial supplements. These workarounds forced them to engage with the world holistically, blending astronomy with ecology, mythology, and sheer intuition. Compare that to today's specialized science, where an astrophysicist might never touch a telescope, relying instead on data piped from a satellite. There's power in both approaches, but the ancients remind us that sometimes depth comes from immersion, not just information. So how can we reclaim this wisdom? Start by stepping outside literally. Put away the apps and let your eyes adjust to the real night sky, just as they did. Track the moon's phases for a month with nothing but a notebook, or learn to spot Venus's 8-year dance between morning and evening star. Visit a local astronomy club and experience the camaraderie of shared discovery, where amateurs still make meaningful contributions to science. Or try replicating their tools. Carve a simple gnomon from wood and mark its shadows at noon, watching as the solstice approaches. You'll gain something no algorithm can offer: the visceral thrill of catching nature's rhythms firsthand. This isn't about rejecting modern technology. It's about balancing it with something older and just as vital: the art of paying attention. The next time an eclipse darkens the sky, resist the urge to watch it through a screen. Stand in its path instead, feeling the temperature drop and the birds fall silent, just as ancient observers did. In that moment, you'll touch a thread connecting you to every culture that ever looked up in wonder. Their legacy isn't just in the predictions they left behind, but in the invitation they extend across time, to slow down, to collaborate, and to let the universe teach you at its own pace. Now imagine taking this further, applying their methods to challenges they never faced. Light pollution obscures our skies today, but citizen scientists are reviving ancient techniques to map its spread, using star visibility as a barometer for environmental change. Schools are partnering with indigenous elders to teach celestial navigation, blending millennia-old knowledge with modern ecology lessons. Even space agencies are studying oral traditions for clues about historical supernovas or meteor showers. The ancients may not have had Hubble's lens, but their way of seeing, patient, participatory, deeply connected, might just hold keys to solving problems they could never have imagined. Want to touch the stars like an ancient astronomer? You don't need high-tech gear, just your eyes, a few simple tools, and a bit of patience. Start by tracking the moon's phases the way Babylonian scribes did. Mark its shape each night in a notebook, noting how it waxes and wanes over weeks. Within a cycle or two, you'll begin to see the patterns they use to predict eclipses. Or try building your own gnomon. A stick planted in the ground becomes a powerful solar calculator. Measure its shadow at noon over months, and you'll discover the sun's shifting path across the seasons, just as Egyptian priests did to align their temples. These aren't just history experiments, they're visceral reminders that the cosmos operates by rhythms anyone can learn to read. For a deeper dive, join the global community of citizen scientists keeping ancient traditions alive. Projects like the Eclipse Soundscapes mission collect audio recordings during eclipses, just as indigenous cultures once documented how animals react to sudden darkness. Others use smartphone apps to map light pollution, tracing how modern skies differ from the star-filled canvases the Maya or Polynesians navigated by. There's even a group recreating the Antikythra Mechanism with 3D printed gears, proving Bronze Age engineering could rival modern clocks. These efforts do more than preserve knowledge. They reconnect us to the participatory spirit of early astronomy, where every observer added to humanity's understanding. What's next for celestial study? The future might look surprisingly familiar. While mega telescopes like the Vera Rubin Observatory scan the cosmos, researchers are also revisiting ancient techniques. Archaeoastronomers laser scanning Stonehenge have uncovered new lunar alignments, while linguists decoding Mayan glyphs found eclipse warnings embedded in royal coronation dates. Meanwhile, NASA has studied Polynesian star compasses to improve backup navigation for spacecraft, proof that old wisdom still holds value in the space age. The most exciting frontier, crowdsourcing. Just as Babylonian temples pooled centuries of eclipse records, platforms like Zooniverse let millions classify galaxies or track asteroid paths, turning amateur stargazers into collaborators on grand cosmic questions. The real lesson from ancient astronomers isn't just about predicting eclipses, it's about perspective. They saw the sky not as a distant mystery, but as a living classroom where every shadow and shimmer held meaning. Whether you're charting Jupiter's path with binoculars or contributing to a global star map, you're part of that unbroken chain of curiosity. The tools have changed, but the wonder remains the same, a humbling reminder that the universe speaks to those who take the time to look up and listen. Those ancient clay tablets and star charts aren't just relics, they're active tools in cutting-edge science. Modern astronomers have made a startling discovery. By comparing Babylonian eclipse records from 3,000 years ago with today's observations, they've detected a gradual slowdown in Earth's rotation. The key lies in the discrepancies. When a scribe in 762 before the Common Era noted a solar eclipse over Nineveh, his timing accurate to the hour now reveals that Earth's spin has lost nearly 4 hours over millennia. This deceleration, caused by tidal friction from the moon's gravity, is so subtle it's measurable only across centuries. Those ancient observers didn't just predict eclipses, they left behind a cosmic clock ticking at the pace of planetary time. But the real breakthrough is how this data is shaping our future. NASA's upcoming Artemis missions, aiming to establish a lunar base by the 2030s, will rely on eclipse patterns to synchronize operations. The moon has no atmosphere to scatter light, so solar eclipses there aren't just spectacular, they're scientifically invaluable. During totality, temperatures plummet by hundreds of degrees in minutes, offering a rare window to study the sun's corona without interference. Ancient astronomers tracked these moments with stone circles and shadow sticks. Tomorrow's colonists will use them to calibrate solar arrays and protect equipment from thermal shock. Meanwhile, projects like the Laser Lunar Ranging Experiment are taking inspiration from the past. By bouncing lasers off retroreflectors left on the moon by Apollo missions, scientists measure Earth-Moon distance with millimeter precision. data that's confirming theories first hinted at in Maya eclipse tables. The same Venus cycles that dictated Mesoamerican wars now help predict gravitational waves. Even Polynesian star compasses, once guiding wooden canoes, are being adapted as backup navigation for spacecraft in case of GPS failure. What's next? Imagine telescopes on the moon's far side, shielded from Earth's radio noise, scanning for cosmic echoes of the Big Bang. Or astronauts using eclipse shadows to prospect for water ice in permanently dark craters, a technique the Inca might recognize from their solar pillars. The stars that guided ancient builders and sailors are now waypoints for interstellar probes, their positions refined by AI but still following paths mapped millennia ago. As we stand on this bridge between past and future, one truth emerges: curiosity is our compass. Whether etched in cuneiform or coded in silicon, humanity's quest to understand the heavens remains unchanged. The tools evolve, the scale expands, but the essential wonder, that urge to look up and ask why, is as old as the first shadow that crossed the sun. And perhaps that's the greatest legacy of those early stargazers, not just the knowledge they left, but the invitation they extend to every generation since. To keep watching, keep questioning, and keep reaching for the sky, because the cosmos still has stories to tell, and we're just learning how to listen. From Babylonian tablets to Polynesian star paths, ancient civilizations didn't just observe the sky. They wove it into the fabric of their existence. Every solstice marked in stone, every eclipse predicted with painstaking precision, was more than a scientific feat. It was a testament to humanity's unshakable determination to find meaning in the cosmos. These stargazers didn't have satellites or supercomputers, but they had something just as powerful: time. Generations of patience passed down like heirlooms transformed fleeting observations into enduring wisdom. The Maya didn't build their Venus tables in a lifetime. The Babylonians didn't crack the Saros cycle in a decade. Their greatest tool wasn't technology, it was the willingness to watch, wait, and let the universe reveal itself. There's a quiet rebellion in their methods. In a world that often values speed over depth, their legacy whispers a different truth: some answers can't be hurried. The Polynesian navigators who memorized wave patterns under open skies, the Inca priests who tracked solstices with shadowed pillars, they understood that mastery begins with attention. Today, we can summon star maps with a tap, yet something profound is lost when we outsource wonder to algorithms. The real magic happens when we step outside, away from screens, and let our eyes adjust to the same stars that guided kings and sailors millennia ago. That moment when you spot Orion's belt or trace the curve of the Milky Way, you're not just seeing light, you're touching a thread that stretches back to the first human who ever looked up and wondered. This isn't just history, it's an invitation. You don't need an observatory to join the conversation. Try tracking the moon's phases for a month, noting how its path shifts. Or visit a local astronomy club and peer through a telescope at Saturn's rings, just as Galileo did 4 centuries ago. Better yet, mark your calendar for the next eclipse and stand in its shadow, feeling the temperature drop as ancient cultures once did. These experiences bridge eras, reminding us that the sky belongs to everyone. The same constellations that inspired myths in Mesopotamia still hang over our backyards unchanged. So as the stars blink awake tonight, remember, you're part of this story. Whether you're an avid stargazer or someone who rarely glances up, the heavens still hold mysteries waiting to be uncovered. Not with billion-dollar telescopes, but with curiosity and a willingness to linger. Share your own celestial moments below, the first time you saw a shooting star, or how your ancestors interpreted the night sky. And if you take nothing else from this journey through time, carry this: the universe isn't just above us. It's within us, in every question we ask and every wonder we chase. The ancients knew it, now